Okay, hi folks, we're starting here with the second video in our section on the first law of thermodynamics. So as I said, this is a pretty massive section. My learning goals, there's actually 17 of them for this chapter, so there's a lot. So let's just talk about what we covered in that very first video, okay? So know the definitions of open, closed, isolated systems, as well as exothermic and endothermic processes. Okay, so hopefully that was, more or less a review from your Gen Chem days. So understand what a state function is and how to identify them. So remember, capital letters are state functions. Okay, and state functions are path independent. Okay, so it only depends on the initial and final state. Okay, know the equations and be able to use them of internal energy of representative gases. So that includes, 3 ½ RT for atoms, 5 ½ RT for linear molecules, 3 RT for nonlinear molecules. Okay, and I didn't do any examples of being able to use those equations, but right, be able to plug and chug and do the appropriate unit analysis and so on. Okay, know the equation and be able to use it of the first law of thermodynamics, right? Delta U is Q plus W. Okay. And then that's what we got through for that first video. Okay. So I'm going to go ahead and close this and come back to that after this video. Okay. And so now I'm going to kind of really start getting into kind of the derivations and more of the math in this chapter. So that last talk was more conceptual. So I'm going to start deriving a lot of relationships here, and there's a lot of equations in this section. So work hard at keeping track of these equations, okay? You might have to make flashcards, but there's going to be a lot of these simple little equations, and I do want you to know them. And mostly what I want you to know about these equations is, like, if I say expansion against constant external pressure, come up with the equation, okay? So we're going to have a lot of these scenarios, okay, that all end up with a different equation because the scenario gives us a different physical relationship. So in this first scenario, we have expansion work, and it's expanding against a constant external pressure, okay? So we have this, like, two cylinders. Let's say the initial state looks like this and the final state looks like this. So you can see in this scenario, the cylinder is expanding, and I'll say it's expanding by height dz, okay, from the initial to the final state. We'll also say the cylinder has area A, and that area is the same from initial to final state. And I'll also say that there is some constant external pressure pushing on this cylinder, okay? And so again, that external pressure is constant, okay? So what we can first say about this system is the following. We know that dW is negative force times dz, okay? Great. And we can also say, so we really know that this constant external force is really, or constant external pressure is really the force due to gravity, right? Let's just suppose this is an open, the cylinder is open to the atmosphere, okay? So if we know pressure is force divided by area, then I can say that this force in question is going to be P external times the area. And again, I get that because I know by definition, pressure is force divided by area. And so I can say then that the work that this cylinder is having to undergo is given by this force acting over this area with, that constant external pressure. Okay. So I can think of the volume of the cylinder. So the cylinder is really undergoing volume changes, right? So I'll write those volume changes as dV. And remember, when I use these little d's, we're talking about infinitesimally small changes so that we can develop these relationships for any number of, subtle changes to this cylinder, okay? And so I know the volume that this undergoes, the change in volume, is going to be its area times dz. That's the change in volume, okay? And I also know that the force that this thing is undergoing is P external times area. So I can plug a few of those things in now. I can say dW has to equal negative PEXA, okay, that I get from the force, and then times dz, okay? And so now if I keep expanding on that, because I know that area times dz is just the change in volume, then I get dW is negative P external times dV, okay? And this gives me the general expression for expansion against constant external pressure, okay? So let's see what I have next. I think I added one more slide in case I need extra room, but I don't think that I need extra room yet, so let's keep going, okay? So this is our general expression, and on one of those learning goals, and I'll review that in a moment, it said know the equations for expansion against constant external pressure. This is the equation, right, that I want you to know. Because from here, you can expand that equation for analysis or for calculation, right? So for example, suppose I wanted to know how much work was done, okay? Well, if I want to know how much work is done, I have to integrate both sides. So if I integrate dW, I just get W. And now I have to integrate P external dV, and I'm going to integrate that from V initial to V final, okay? Well, this is a pretty simple integral. We know P external is a constant, so it can just come out the other side. And then the integral of dV from V final to V initial is just going to be V final minus V initial, okay? So that looks something like this. So work equals negative PEX times V final minus V initial, okay? Or in other words, for this constant external pressure, right, this relationship just simply reduces to negative PEX times delta V. Okay, I put a little thick line there so you know that it's a delta. Okay? So either of these equations work, right? But you can see quite simply because my pressure is constant, it doesn't influence this integral. Okay? So now why the negative sign? Well, let's think about this for a minute. So in this picture, we're undergoing expansion, right? It's expanding against this constant external pressure, okay? So now what happens to the volume, okay? Well, volume initial is smaller than volume final, or in other words, the quantity delta V is going to be positive in this picture, okay? So a positive quantity times a negative quantity gives us a negative quantity, okay? And thus expansion work is exothermic because we recall when the sign is negative, right, that tells us it's exothermic. In other words, if this is the system and up here this P external is the surroundings, my system is pushing away the surroundings. My system is doing work on the surroundings, okay? Well, what if it was compression? Let's see, do I have any room? So I'll write this over here. So what if it was being compressed? Well, if it was being compressed, you know, then it would go the other way, initial and final, okay, that way. Oops, let me erase that because that's going to be confusing when you go to look at this later on, okay? So I know what I'm going to do. Let's go to the next slide. Yes, I left myself more room. So now let's suppose, okay, let's get rid of that. Let's call this the initial and this the final. So we still, you know, have the same thing going on. This is dz, this is a, this is a. There's some constant external pressure, that's the same from initial to final, right? Because it's really due to the pressure of the surroundings. And that equation said negative P external times delta V, which we know is negative P external times V final minus V initial. So in the case of compression, okay, the volume final will be smaller than the volume initial, so I get a negative term. Negative negative gives me a positive, and that is endothermic. Okay, so that means, in other words, now when the system has to undergo compression, the surroundings are pushing on the system. All right? And if we think about the work done in this scenario, I'm going to draw kind of a rather crude coordinate system, a crude graph that we'll come back to in a bit. So if I plot this as P versus V, so here's my PEX, okay? And then perhaps this is V initial and this is V final. All right, and if you look at the product of this, it's just pressure times volume. So on the scale, when I have pressure times volume, it makes a rather simple looking graph. It's just this box, okay? And the area under this curve, this box, represents, oops, let me draw a different color. Okay. So the area indicated by this box is the work done, right? Because it's just simply the product of pressure versus volume, okay? And we're always at this external pressure, right? So whether you move this way or whether you move this way, right? Whether it goes, the volume expands or whether it compresses, this total work done is the same, just opposite sign, depending on whether it's compression or expansion, okay? So now what about free expansion? I left myself a whole lot of room just to simply write work is 0 in free expansion, right? Because there's no opposing external force. So no opposing external force. So anytime a gas expands into vacuum, it doesn't do any work, okay? So that's simple enough, all right? Okay, moving on. Okay, so still more on expansion work, but now let's get into reversible expansion, okay? And here, this is where the equations are still going to be simple equations, but in the world of thermo, it's the language that gets tough, okay? So let's first by defining what reversible means in thermo. It's a change that can be reversed by an infinitesimally small variation. And a good example of this is thermal equilibrium. So suppose I have two chambers, okay, and suppose they're separated by a diathermic wall, okay? Well, if this chamber is at T1 and this chamber is at T2, we recognize that energy or heat will flow, okay, between those two devices between those two chambers, if T1 does not equal T2, okay? And so if T1 does not equal T2, then heat will flow depending on which way it needs to, depending on which one is greater, right? Heat will flow from the hot object to the cold object, okay? And using this kind of language of calculus, and I don't want you all to be too terribly concerned or confused by this, but all this is saying, by saying this is reversible, let me finish writing this relationship, T2 plus or minus dT2, which is much greater than that absolute value. So all that it's saying is, okay, This infinitesimally small variation, that's what it is. Okay, so T1 plus or minus dt1, that's this infinitesimally small variation. And because that's infinitesimally small, this quantity is going to be much, much greater than what that change is in the first place. Okay? So reversibility means simply if T1 becomes just slightly warmer than T2, it becomes slightly greater in temperature than T2, heat will flow this way until both of them are at the same temperature. Okay? Same with T2, the opposite is true. Okay? So now, what about reversible expansion work? Okay, let's keep going with that. So dW equals negative P external dV, and I'm going to define that as irreversible. I can't spell right now. Bah, I just got blanked out. I'm listening to my son yell and scream and play outside. I don't know if you guys can hear that or not. As a parent, you can like hear your child yelling from any distance away. Okay. Irreversible. Why did I write irreversible on that equation right there? So remember, this is the equation for expansion against constant external pressure. Let's back up to that for a second. Okay, with this picture right here, right? Whether I'm going expansion or compression, either way, once my system achieves mechanical equilibrium with the surroundings, that means the pressure inside the system will be the same as the pressure of the surroundings. So now there's no more difference between the pressure of those two areas. And so there's going to be nothing that allows it to become reversible unless, of course, I do some type of chemical reaction in here that generates pressure, but that would no longer be expansion against constant external pressure. Okay? So it follows that expansion against constant external pressure is always irreversible. Okay? So how do I write reversible expansion? Well, I can simply say dW equals negative P dV reversible, assuming I can spell. And thus, we have to think of how P depends on V in the reversible expansion. Okay? So in other words, when I calculate irreversible expansion, so I should have left myself space. I'm going to draw an arrow down here. Okay? To calculate irreversible work, we just recognize it's simply work equals negative P external times change in volume. Okay? To calculate the amount of irreversible work. And we should also recognize that this is in the unit Pascal, and that's in the unit cubic meter, then I will get a joule. Okay, don't forget the dimensional analysis units. Okay. What about calculating work for reversible changes? Aha, well what I have to do is the following. Work equals negative integral P dV integrated from volume initial to volume final, and I can't pull the P out of that integrand. I have to actually integrate it. Okay? So that represents, as far as calculation, how we calculate the work done reversibly versus how we calculate work done irreversibly. Okay? So let's keep going and do an example here. Okay? And so what I'm going to prove on this slide is that reversible expansion work is always greater than irreversible expansion work. Okay? So how is that so? So let's use, so as an example, isothermal reversible expansion. And I'm going to use for an ideal gas. Okay, and here I can call up my equation of state for an ideal gas, right? P is nRT over V. And so for now, we're going to say make N and T constant. So this could be in a closed system where energy is free to exchange but not mass. And isothermal means we're also fixing the temperature, okay? Just for now, to make this an easier example, all right? So now if we know that we have to do, right, work is this equation. Okay, let me take a drink of water. Well, we have an equation for P, right? So we can plug that in. And so that equals negative VI to VF integral. And that's going to be nRT over P. Oops, excuse me. nRT, let me write that a little bit better. nRT over V times dV, okay? Where now we should recognize that N, R, and T are all constants. Because for one, in the scenario, okay, this is another one of these scenarios that I want you to be familiar with, isothermal reversible expansion. In this scenario, N and T are constant. Okay, so that means my integration is pretty straightforward. Negative nRT just times the integral dV over V. Pause the video for a second and just see if you can complete that integral. It's not too bad. You should not even need Mathematica for that one. Okay, see if you can remember how to integrate dV over V. I'm just going to go ahead and give you the answer. It's negative nRT. And then, of course, when I also apply the limits, VF and VI, I get natural log of VF over VI. So recall, the integral dV over V is just natural log of V. Okay? So this is now my equation for calculating work done isothermally and reversibly. Okay? So how is it that reversible expansion is always greater than irreversible expansion? Well, let's go back to this picture I drew, that simplified picture, right? VF over VI, right, where we realize it can go expansion or compression. It doesn't matter. So this area right here represents our irreversible work. Okay, just this shaded area. Oops, I'm not going to do that. I'm just going to say this brown area represents only our irreversible work, okay? Because pressure is fixed. It's only going to be like, you know, along that pressure line, okay? Well, what about the irreversible work? Or excuse me, reversible work, the reversible expansion. Well, here's the equation, PV equals nRT, right? P versus V, Boyle's law, right? It goes like this, okay? And so the reversible work not only contains the area in this yellow part right here, but it also contains the irreversible area as well. It contains both of those areas, okay? Because it has to be the full area under the curve, right? So if I take the whole area under the curve, not only do I have this chunk, but I also have this chunk too, okay? So doing expansion work reversibly not only has the quantity of work that would be if it were irreversible, but it contains an extra quantity needed to ensure that it be reversible, okay? So it follows that reversible expansion work is always greater than irreversible expansion work, all right? What about a van der Waals gas, okay? What about it? So I'm not going to do this, but you should try it. And this one is not too bad at all, right? I'll set this up again. We know it's just a simple equation, P dV. But now what does P equal for a van der Waals gas? Well, it's N R T over V minus NB minus A times N over V squared. Okay? So when you put in this value here, right, you're going to integrate this whole expression. It's not so bad, I promise. I'll give you the solution. And the solution is very similar to the solution for an ideal gas. We still have this term, negative nRT natural log, but now instead of it just being simply VF over VI, it's VF minus NB over VI minus NB. And then you have this extra term, minus A N squared 1 over VF times the quantity 1 over VI. And this becomes our isothermal reversible expansion for a van der Waals gas. And now the question is, does it require more work to reversibly expand a van der Waals gas or an ideal gas? Well, that depends on what regime you are in. If you are in the regime where attractive forces dominate, it will be more work to expand a van der Waals gas, right? Because the molecules are being attracted to themselves and you have to pry them apart. However, if you're in a regime where repulsive forces are dominating, where the molecules don't want to get close to each other, it will take less work to reversibly expand a van der Waals gas than an ideal gas, okay? So it's condition specific, right? Okay. But the important take home is reversible expansion work is always greater than irreversible expansion work because the reversible expansion work contains the area under the curve of irreversible plus its own area for the reversible work as well, okay? So hopefully that's clear. Okay, moving along. So let's get into heat transactions. So this is now where we're going to start getting into hopefully also some familiar ground, talking about calorimetry and heat capacity. Okay, so for now, this is, you know, another one of these scenarios, constant volume process. Okay, we can also talk about a constant pressure process. So this is kind of the game we play, simplifying our scenario, right? Defining what we're dealing with here. In this case, let's just talk about a process that's constant volume, okay? So it can be shown quite simply that the internal energy of a constant volume process is just Q, because for a constant volume process, let me write this, let me write this for infinitesimally small changes. dW equals, du equals dW plus dQ. So for all constant volume processes, work will equal 0. If there's no change in volume, there's been no work done, okay? And so du will equal dQ, or delta U will equal QV, all right? And something I want you to get used to in this class, the subscript that we put down there denotes that something's being held constant. So when I put a V, and I meant that for it to be a capital V, okay, as volume is a state function, then that denotes that volume's constant. Okay, so again, let me write that down. When I write QV, that's heat at constant volume. The V indicates volume is constant, okay? So we can study this process via calorimetry, the study of heat transfer, okay? And so we can write QV as the following: CV times delta T, where CV is my constant volume heat capacity. I'm not writing constant volume down there because that little V down there tells me that it is constant volume, okay? And then we recognize that delta T is the change in temperature, T final minus T initial. So this heat capacity, CV, has units of joules per Kelvin, and then temperature is Kelvin. So this just gives me units of joules. So that's the extensive parameter. So in other words, if I'm talking about the heat capacity of 1 gram versus 100 grams, that matters, right? 100 grams of material will be able to absorb more heat than 1 gram of material. But what about intensive? Okay, so for intensive, we use the specific heat, okay, which has units of joules per gram per degree Kelvin, or some of you are probably used to seeing that as joules per gram per degree C. It's the same thing, right? Because the change in temperature for 1 degree Kelvin is the same in temperature for 1 degree Celsius. And of course, this mass here would be the, I should have wrote lowercase m, apologies, but we'll just say mass of material in grams. So not the molar mass, just the mass in grams. And so, right, when I multiply all those units together, that also gives me joules. Okay? So you're probably far more used to seeing this intensive version of the equation, right, with specific heat, joule per gram per Kelvin, okay? But we also can have this extensive, just joule per Kelvin, right? And so with our specific heat, so what this all means, so I'll give you an example here. So we know water, I'm running out of room here. So we know H2O liquid is 4.184 joule per gram per Kelvin. And so what that means is if I have 1 gram of liquid water and I want to raise its temperature by 1 degree Kelvin, I need to supply it with 4.184 joules. Okay? So if we look now, the definition of heat capacity, so by definition, heat capacity is the partial, and don't forget what partial derivatives are, okay? Partial of U with respect to the partial of T at constant volume. Okay, at constant V, okay? So what does this mean? Well, if I have a slope of U versus T, I get a relationship. And for now, I'm just going to kind of draw you a simplified relationship. It looks something like this, okay? So the slope of this line is the heat capacity, okay? Slope equals CV, all right? And there's something really cool that happens related, let me draw this arrow a little bit more clear. Related to the equipartition theorem, there's something really interesting going on here, okay? If we look at a really vast range of temperature, so perhaps like, 0 Kelvin to, I don't know, 10,000 Kelvin, right? Some giant range, okay? The relationship of internal energy with temperature is not going to be linear. So there's some kind of curvature going on here, okay? And we're going to get into that detail soon. But if I look at the range that I'll call, approximately room temperature, 298 K. And by approximately room temperature, that spans some region like A to B. Then the heat capacity, assuming I can draw this, oh yeah, that's good. Heat capacity will be somewhat constant. I should change the color of that so that's like really clear, okay? So over some range, thereabouts in room temperature, that slope of U versus T will be constant, okay? And for now, just think of it as, 298 plus or minus, I don't know, 50 or something, okay? I don't want to put a hard range on that yet, but we'll just say, at approximately room temperature, heat capacities are constant. So for example, this specific heat of water, right? That's the room temperature value for the specific heat of water. At a different temperature, that value is different. However, there is a nice range, a fairly large range, where U versus T has a constant relationship, and thus you can use a single value of heat capacity. Okay? So let's do another activity. Come up with expressions for the heat capacity for a representative monatomic gas, linear molecule, and nonlinear molecule. How does heat capacity of a nonlinear molecule compare to that of a monatomic gas? So it's the same activity I had you do before, but now you're coming up with heat capacity. So feel free to pause it if you need to. I'm just going to go for it, okay? And I'll remind you that CV equals the partial of U by the partial of T at constant V. So remember, a monatomic gas, UM as a function of T equals UM 0 plus 3/2 RT. So how do I use that in this relationship? Well, recall, with partials, okay, I can say now, okay, partial with respect to T, and I'm going to supply my equation for U, okay, which is UM. I'm going to start writing, instead of UM as a function of 0, I'm just going to write UM 0 up top right there, okay, plus 3/2 RT. So, and then that's all that constant V, and I could put that little V down there being constant, so I would know the V is being held constant if I wanted to. It's a little redundant. The mathematicians will tell us we don't have to do that, but chemists, we like to put the variable that's being held constant, okay? So this is a very easy derivative. This is a constant, so when you take the function of this with respect to temperature, it's 0, and the derivative of 3/2 RT is just simply 3/2 R is the heat capacity for all monoatomic gases. Not the specific heat, just the heat capacity, CV, okay? So what about a linear molecule? Well, we remember linear molecule, I'm just gonna simply write this, was 5/2 RT, and nonlinear molecule was 3 RT, right? So now CV for a linear molecule is going to be ddt of 5/2 RT, which is just 5/2 R. Okay. What about the nonlinear molecule? ddt of 3 RT is just simply 3R for a non-linear molecule. Okay, how does the heat capacity of a nonlinear molecule compare to that of a monatomic gas? 2 times. It's 2 times the difference. And what does that mean? That means to get the same rise in temperature, a nonlinear molecule has to be supplied twice the amount of energy as a monatomic gas. So for example, suppose I want to heat up argon by 1 degree Kelvin. And let's say I have 1 mole, okay? So to get the same situation for, let's say, water and, steam, right? If I wanted to heat up steam, 1 mole of steam by 1 degree of Kelvin, 2 times the energy must be supplied for the water than for the argon, because of the degrees of freedom, right? Because the nonlinear molecule has more degrees of freedom that heat has to be pumped into to actually get a temperature rise, okay? So now we're starting to learn about the secrets of the universe. And let's even keep going with this, okay? So heat capacity of solids, all right? So there's some gross looking equations on here, but hopefully you all might recognize some of this. So let's digest this, okay? So the heat capacity of all solids is given by the Einstein equation. So this E right here is E for Einstein. Okay. We could also replace it with a D, and that would be for Debye. And you can see here the two competing equations of Einstein and Debye are very close. Debye actually got it right. So these values are measurements. And I'm not going to get into too much detail in the difference between the Einstein heat capacity of solids versus the Debye, because they're both very close. So we'll look at the Einstein equation. Okay, so what it says, it's the quantity 3 times R times this function of T. Okay? So let's talk about why 3R. So if I have a solid, okay, in some lattice, right? And I'll just put like one little, atom or something like that. Suppose we're just talking about something really simple like silver or lead or iron or something, okay? Well, we know in the solid, it's not going to be free to translate. It's not going to be free to rotate. It can very subtly vibrate against the other lattices, okay? It's very subtle. It's a very, very low energy vibration. If you recall from your FTIR days in OCHEM, those solid vibrations will appear way down in the fingerprint, like 500 wave number and below. And as it turns out, that makes them low enough in energy to matter for equipartition. And in a gas, whereas we said there's 3 degrees of this translational freedom, right? It can move X, Y, Z. Well, the solid, when we think about the solid kind of vibrating against its other, neighbors, that is kind of like a translation in some ways. It's trying to move, right? Let's say it's trying to move out in this direction. But of course, as soon as it moves in that direction, it's going to hit, it's going to be really close to another neighbor. So it's going to want to influence it to go back the other way. Okay, so that's what's going to give it that vibration. Similarly, it would happen in this coordinate, and it would also happen in this coordinate. So how many degrees of freedom does that represent? If you said 3, you're not thinking 3-dimensionally. Because remember, in a gas, the next nearest neighbor is way far away, like down the street 10 million miles away, practically, right? So whether a gas moves in a positive X or positive Y, or positive X, negative X, positive Z, negative Z, whatever, right? Those are degenerate. They are not for a solid, because a solid has neighbors, okay? So we get 1/2 RT for each and every one of these motions. Okay? So the positive X and the negative X are no longer degenerate in a solid. So that's 1, 2, 3, 4, 5, 6 degrees of freedom, 6 1/2 RTs gives me 3 RT. And remember, partial of U by partial of T equals the heat capacity, which is 3R. Okay, so now, in the heat capacity of solids, CDM equals 3R times this function. So that's where the 3R comes from. But what is this function? Well, I hope you've been staring at this long enough to think it's a partition function. Right? Let's look at this. E equals theta E divided by 2T, where theta E is h nu over kb. Let's plug that in, okay? So E raised to the power, so that's exponential, raised to the power theta divided by 2T. That's going to be E raised to the power h nu, and look, divided by 2T, that's going to be 2K Boltzmann T. Oh my God, that's it. That is a partition equation. And what does this theta E represent? That is what we call the Einstein temperature. Okay? And as it turns out, the Einstein temperature, so if you look at my scale here, so this is, again, another reduced variable space scale. So this number 1, when this is 1, that means the temperature equals the Einstein temperature. Okay? And so I'll give you an example, because I know it off the top of my head. For lead, the Einstein temperature is roughly about 105 Kelvin. Okay? And so we would get that by saying H times, so this is the frequency of vibration. Okay, so that is, so look, H nu, right, gives me energy. Okay, E equals H nu, right? Don't forget that. Okay, and so this is all energy divided by K Boltzmann T. So that's the frequency, I'll just say freq of vibration. So, and that's in hertz. That's in units of 1/seconds, because my Planck's constant, right, is joule seconds, okay? So, those vibrations, it's going to be something like, 10 to the 12 hertz or something like that, corresponding to about 500 wave number, the fingerprint region. So if we go and calculate that, each solid has its own Einstein temperature because its vibration and its lattice is unique. So for lead, this would occur around about 105 Kelvin. And if I follow this up here, look at this, okay? This scale is CV divided by R. So, right, that's 1R, 2R. So here's, I'll put in parentheses, 3R is the top of this line. And look, the Einstein temperature is this temperature at which the solid approaches its bulk classical heat capacity. All right? So in other words, at 298 K, this equation just becomes 3R. Because at 298 K, this partition function no longer matters. That partition function approaches the value of 1. Okay, so in other words, above the Einstein temperature, there's sufficient population of states that all of those vibrations can be accessed and populated, okay? And thus our heat capacity will exhibit its bulk characteristic heat capacity, which is 3R for all solids. And you might be thinking, how the hell is the heat capacity 3R for all solids? Well, check out how this works, okay? Look, it's 3 times 8.314 joule per mole K, which equals, the quick calculation, I meant to have a calculator out in front of me for this lecture. So 3 times 8.314 gives me, I'm just going to write about 25 joule per mole K. So how is it that all solids have the same heat capacity? Well, remember, it's the specific heat capacity, the joule per gram per Kelvin, that gives us that unique value, okay? And so, for example, if I want to calculate the specific heat of lead, let me look up the molar mass now, of lead is 207 gram per mole. So I'm sorry, this is getting a little sloppy here. So now I know in 1 mole of lead, it's 207 grams, okay? So the specific heat of lead is about 0.12 joule per gram per Kelvin, okay? Which would be different than the specific heat of iron or of manganese or whatever, right? So the heat capacity of all solids is 3R once you're above the Einstein temperature. However, you have to remember the specific heat is different. And I'm going to do another cool example here talking about the heat capacity of liquids. And you can tell by my picture, I'm specifically going to use water in this example, okay? So Let's do this example from kind of working backwards. All right. So let's first start with liquid water. We know the specific heat of water is 4.18. I'll say 4.184 joule per gram per Kelvin. We know that's the same as joule per gram per degree C. Okay. What if I now want to convert this into joule per mole? Well, I know water is about 18.01 grams per mole. So when I do that with 4 sig figs, okay, I get 75. Oops, let me make sure I hit that in right. Yes, I get 75.35 joule per mole per K. Okay? And so we'll back up and we'll recognize that, right, heat capacities, CV, are some constant times R. Okay? So I'll put in some constant C times R. So for a solid, it's 3R. For a monatomic gas, it's 3/2 R. For a nonlinear molecule gas, it's also 3R. So what about for liquid water? Okay. Well, if I know that this is the specific heat, 75.35 joule per mole K, or excuse me, rather, the specific heat is 4.184 joule per gram per Kelvin, and I know the heat capacity is this value, 75.35 joule per mole K, then what is this constant? Well, divide 75.35 by R, okay? So let's do that, okay? So I'm gonna divide that number by 8.314. This is awesome. I get 9.06. Now, some of you are like, why is that awesome? Why is that significant? Well, it's damn close to the whole number 9. Damn close, okay? And the reason why it's not exactly 9 is because this is the equipartition theorem. So what's significant about the number 9? Okay, well, if CV for liquid water is 9R, how many degrees of freedom does that correspond to? Well, it would have to correspond to 18 degrees of freedom, right? 18 1/2 R gives me 9R. Where does that 18 come from? This is awesome. Here's the water molecule, okay? There's a hydrogen, there's an oxygen, and there's another hydrogen, okay? And then we know from this picture, right, that it's in this like really complicated, always changing hydrogen bonding network. So hopefully I've drawn this thing big enough to make sense out of this thing. Actually, I think I'm gonna pick on, can I pick on one of those? No, I need to draw my own to make this. Okay, I'm gonna draw this bigger. There's my very cartoon, crappy looking water molecule. Okay, so I'm gonna do a different color. And let's make a coordinate system. So we know that this hydrogen, it can move forward, backward, left, right, up, or down. Okay? And so that motion, so imagine like my torso is the oxygen, right? And each of my hands are the hydrogens, right? We know water can vibrate like this symmetrically. We also know it can vibrate like this asymmetrically. We know it can undergo the rocking motion or the bending motion, okay? So all of those give us this three-dimensional coordinate system on each one of these atoms. So each one of these atoms are really free to move forward, backward, left, right, up, down. Forward, backward, left, right, up, down. That's 6 degrees of freedom per atom 6 DOF per atom, and there's 3 atoms in the water molecule, giving us 18 degrees of freedom, giving us 9R for the value of heat capacity. And if I go and calculate, and you know, I did this backwards and we get 9.06. So if I go the other way, suppose I just calculate 9R, 9 times 8.314 gives me 74.826, okay? And then now if I divide that by the molar mass of water, 18.01, I get 4.155. That's really damn close to the specific heat capacity of water, the measured heat capacity. So obviously there's, you know, this model doesn't account perfectly for that. And we should also recognize when something is chaotic as liquid water, right? It's not so simple to just say like, well, assume each molecule moves like forward, backward, left, right, up, down, and then just say that times 6, right? But it's damn good. It works really well, okay? And so this model will fail for much, much larger molecules because the interactions become a lot more complicated than just up, down, left, right, forward, backward, okay? However, for these simple molecules, for liquids, this works really well. For the solids, this also works really well, okay? So for all liquids, or for the simplest liquids, it's the specific heat capacity, and then kind of work backwards into the degrees of freedom, which for water is easy to do. For other more complicated molecules, not so much. For solids, 3R. 3R for the heat capacity. And that is, of course, above the Einstein temperature, right? And then for gases, 3FR for monatomic gas, 5FR for linear molecule, 3R for nonlinear molecule heat capacities, okay? I think that's a pretty good place to end it. And we'll get into talking about enthalpy in the next lecture. All right, folks, thanks for tuning in.